When we talk about a function, we often implicitly mean a function of y in terms of x. We graph such a function on an xy plane and usually make the x-axis horizontal and the y-axis vertical, so we have the dependent and independent variables arranged like this. As we move our inputs along the x-axis, we graph the corresponding outputs to draw the graph of the function. Suppose, however, that we only graph the output, in other words, the range. Let's put another copy of the y-axis here, and don't focus on the original graph. It's there now just for reference. As we move inputs along the x-axis, our outputs are traced on the y-axis, generating this line segment. You might wonder why we want to do something like this, and we find an answer when we change from a one-dimensional to a two-dimensional codomain. This line segment is the graph of the original curve if we graph only the values that the dependent variable attains. In other words, this is the graph of the range. With a function whose codomain is one-dimensional, for example, a line, this isn't too exciting, but we can do the same with a function whose codomain is two-dimensional. Recall that the codomain of a function is the set in which the range of the function lives. The codomain is often a matter of convention, since we can always think of the range as being in a larger set. For example, the codomain of the function x squared is usually taken to be all real numbers, even though we could restrict it to the interval from 0 to infinity, in which case the codomain equals the range. Or we could expand the codomain to be an entire plane. Let's now consider a function whose outputs live in two dimensions. Let t denote the independent variable of a function f of t. The outputs of f of t will be ordered pairs, so we can write f of t equals the ordered pair x of t, y of t, where x and y are both functions of t. For example, let f of t equal cosine t sine t. Let's graph this by following the example we saw at the beginning of the video. We'll put a copy of the independent variable's axis here, and we'll graph the range here in the xy plane. We'll let the independent variable range from 0 to 2 pi. As we increase t, we see that we trace a circle in the plane. We know that a circle in the xy plane can't be expressed as a function of y in terms of x, since it fails the vertical line test. But we see now that we can express the curve using a parameterization, which is a function whose range is the circle. Not only that, but we've given the circle a counterclockwise orientation. If we wanted to, we could change cosine to negative cosine, and thereby change the orientation to clockwise. For those of you who are comfortable with three-dimensional space, we can also see this circle as a projection. If we graph the independent and dependent variables on one graph in 3 dimensions, we get a helix. We can then project this onto the xy plane to get the graph of the range, which is the circle we saw before.